Yeah, and please mute your mic if you're not speaking. Okay, can everyone please mute their mic?
Yes. Hi, everyone.
Okay. Okay,
Hi,
well,
everyone.
hi, Ji. Okay, we can see you. Okay. Okay, I'll just give it 1 minute before we start, and we'll start. I'm not sure who's controlling the slides now, but we're going to start with Soheil. So in a minute, Soheil, maybe you can pull up your slides and start us in a minute. Let's just give it a minute so everybody who wants to join, joins. Okay, let's get started. Welcome everyone, and thank you for sticking around for the second breakout session of the Transportation, Air Quality and Health Symposium for CARTEEH. This session will be highlighting some of our students and early career researchers from the different partner institutes for CARTEEH. Every presenter is going to have 10 to 12 minutes to show and talk about their slides. I'm going to give you a couple of minutes warning by turning on my camera. So if everyone can please turn off their camera for now and only turn it on when they're presenting, that would be great. And I'll give everyone a 2-minute warning before their time is up. And we'll take questions immediately after each presentation. So if all the attendees can send their questions into the questions and answers chat box or the public chat box, I'll moderate them after each talk. So we're going to start with the first presentation from Sohrabi at the Texas A&M Transportation Institute and the Texas A&M School of Engineering as well. And he will be talking about transportation technology and public health, some of the work he led on assessing the health impacts of automated vehicles. So Soheil, you can start, but please put your screen on full screen mode.
Yeah, thank you, Haneen, for the introduction. My name is Sohrabi. I'm a graduate research assistant at TTI and a doctoral candidate at Zachary Department of Civil and Environment Engineering. Today, I'm going to present my work on automated vehicles' impact on public health. I believe you already have enough discussion about the connection between transportation and public health in past 2 days at CARTEEH Symposium. So we know transportation can affect public health. And also we know that there are new transportation technologies that can impact transportation system. One of these technologies with lots of researcher and media attention is automated vehicles. When I'm talking about automated vehicles, I'm talking about level 4 and 5 automation, which are basically now they are actually known as self-driving car or driverless cars. This is something I'm referring to when I'm talking about automated vehicle. When we talk about automated vehicle or self-driving cars, what comes into mind is the convenience of automated vehicles. You can sit in your car, have whatever you want, the activity you want to do, and get to your destination. This is convenient. When we talk about automated vehicle, we talk about their safety. They are safe. They can observe the environment. They can make mindful decisions, and they can prevent crashes. When we talk about automated vehicle, we talk about their capabilities to use the road capacity optimally. So they can, they can be used in platoons and they can increase the road capacity. Also, automated vehicles are great opportunity for shared mobility because they can take passengers and get them to the destination without any human driver interruption. But automated vehicle can change the transportation system, and they can actually affect transportation system. There are lots of discussion and review papers on this area, which you can see in this table. This is a summary of review papers on automated vehicle implications. But an overview of these review papers showed that to us that the discussion about AV's public health implication is still in its infancy, and there is limited awareness about the AV's potential impact on public health. This urged us to just come up with a conceptual model to be able to systematically identify the pathways through which automated vehicle can impact public health. So to come up with this conceptual model, first we summarize the AV's impacts on transportation system through these 7 points of impacts. As you see, automated vehicle can affect transportation jobs because we don't need drivers. If we have less crashes, we don't need body shops. They affect transportation equity. They enable elderly and people with no license, driving license, to drive vehicle, actually ride vehicle and get to the destination. They affect traffic flow, land use, trip mode and route choice, transportation infrastructure, and traffic safety. Then we looked at the pathways to which transportation can affect public health. So this is actually the result of a research conducted by CARTEEH, led by Haneen Khreis, which identified 14 pathways to which transportation can be connected to public health. One can be access, transportation provides access to activities, to food, to healthcare, and everything. So this is one pathway through which transportation can affect public health. Mobility independence, social exclusion, contaminations, greenhouse gases, community surveillance, and so on. So we use the information that we gather from the review papers and from the overview of the review papers on the impacts of automated vehicle on transportation, and the existing knowledge from CARTEEH on the pathway through which transportation can affect public health, and just connected those using, as you see, these lines show the connection between the transportation implications and pathway through which transportation can affect public health. For example, here we have transportation jobs. Automated vehicle can eliminate some jobs, so it will result in social exclusion, and social exclusion is related to some mental issues, for example. I'll give you some examples of the pathways in following slides, but here is the conceptual model we developed to systematically identify the impacts of automated vehicle on public health. As a result of this conceptual model, we could identify 32 pathways between automated vehicle implementation and public health, through which 17 pathways were associated to adverse impacts. It means automated vehicle can negatively impact public health. 8 pathways were attributed to positive impacts, and 7 pathways we don't know how they impact public health, and there are uncertainty in the impact. Here is one example of the pathways. So automated vehicle can change the trip, mode, and route choice. Let me give you an example. This is a classic example in transportation. So we have 40 people. They want to go from point A, the start of the street, to the end of the street. And they use the card. As you see, they can occupy the whole space in the street. They can just use bus, and the occupation would be, the space occupation would be in size of a bus. And they can use bike, and in that case, they are doing physical activity on top of, reduction in the occupancy of the road. They're doing physical activity as well. So back to the pathway. Automated vehicle can change the trip, mode, and route choice. They're more convenient. People, they're more convenient because you can do other activities when you're on your way to work or to home. So this convenience will lead to modal change, and people would change their mode of transportation from public transit to private cars or automated vehicles. This would result in increasing VMT, vehicle mile travel, in the system. If we have more vehicle mile travel in the system, we have more air pollutants. And air pollutants are associated with respiratory diseases, cardiovascular diseases, skin issues, cancer, and childhood asthma. So this is one pathway through which automated vehicle can negatively impact public health. I have another example for positive impact. So automated vehicle can enable elderly people, people with mental and physical disability, and people with no license, like underage students, to use this mode of transportation to participate in activities, go to grocery shopping, access food, access medical care. So this is referred to as mobility independence. And mobility independence, actually, this is not right. So this is associated, it was associated in the literature with mental health and obesity, of course. So this is one way that automated vehicle can positively impact public health. Another pathway I want to talk about is uncertain impact. So people talk about automated vehicle and their safety. They're supposed to eliminate driver error-related crashes. According to NHTSA, 94% of crashes are because of the driver error. And we can speculate that 94% of crashes would be eliminated. But there are safety challenges associated with automated vehicle. Here I listed my result. This is the result of another paper I work on, which shows 5 challenges in AV safety. One can be riskier driving behavior of AV user. Years ago, when we had seat belts, people changed their behavior whenever they were wearing seat belt. They drove more aggressively because they were presumably they were assuming that they are safer and they can be involved in crashes with no harm, but it wasn't correct. So the impact of seat belts was actually adverse at the beginning. So it might happen for automated vehicle as well. We call it in traffic safety engineering, we call it risk homeostasis theory. It needs to be studied in the future, but this is a possibility that automated vehicle cannot be the challenges that the automated vehicle can face. The other one is system malfunction. The whole system, the whole autonomous driving is based on reading the environment and having a detailed perception about what is going on around the vehicle. And it has been done using sensors. And if sensors doesn't work, how automated vehicle can manage the driving tests? So system malfunction is another challenge, safety challenge. The other one is human driving and AV interaction in mixed traffic. So automated vehicle, in a 100% market penetration, when we have only automated vehicles on the road, we don't see any safety issues because they can coordinate, they can, nothing unexpectedly can happen. But when we have a human driver, for example, one impaired driver, one DUI driver, they can do something unexpectedly, and automated vehicles are not programmed for those situations. So this is another safety issue. Another safety issues is related to cyber security issues or emerging safety issues associated with AVs. Hacking, cyber security is something that researchers are working on, and this is a danger that can jeopardize the automated vehicle safety. The other one is the impact of changes in transportation system. Actually, this is indirect impact on safety. Assume that we just had an example that automated vehicle can increase the vehicle might travel in the system. When the vehicle might travel in the system increases, the exposure to the risk of crashes will increase. So if we have more vehicles, we have more chance of having crashes. This is another thing, another safety challenge that the automated vehicle can encounter. So having that said, automated vehicle can eliminate driver error-related crashes, but there are some safety challenges associated with them. And we don't know what happens in the future. If we have automated vehicle, again, I'm talking about level 4 and 5, if we have them on the road, what happens? Does the motor vehicle crashes increase or they just decrease? So this is an uncertain impact of automated vehicle on public health. What we need to do, we have uncertainty in the impacts, and even when we can actually decide what is the direction of the impact, either it is positive or negative, we don't know the extent of the impact. So we need to do quantification analysis. So far, there are not enough studies, or I would say there are just a handful number of studies that quantify the AV impacts, and there have limitations that are based on assumptions. So we need to do some serious analyses. This is a framework I developed as part of the book chapter I wrote for the International Encyclopedia of Transportation. Here, I show how we can proceed with quantifying the AV's impact. As you see, it is a complex process, and it requires knowledge from different fields. So this is a multidisciplinary effort. For example, to capture the changes in transportation after AV's implementation, we need to do travel demand modeling, which usually transportation engineers do, crash prediction modeling, traffic safety, exposure response function, which is a field developing exposure response function, which is in the field of public health and epidemiology science, air quality, noise, and heat models, which lies under environmental engineering, urban growth models, which is part of urban planning. So this is a multidisciplinary effort. And even we need to have an accurate perception about AV's functionalities, the technology, and how it would be implemented, adoption rate, how many people with access to automated vehicle, and the policies and the stakeholder needs. So these are issues that lies under public policy science.
Please let's show.
Yeah, go ahead, please.
No, yeah, you're finished. I'm saying please let's wrap up, but you're already wrapping up.
Yeah. So in a project at Texas A&M Transportation Institute, we are working on two pathways through which automated vehicle can impact public health: air quality and motor vehicle crashes. We want to quantify the health impact of automated vehicle through these two pathways. This project is awarded by Robert Wood Johnson Foundation and Safety UTC, and a group of researchers at Texas A&M Transportation Institute are working on it. Another thing I wanted to mention, I don't go into details, is that we need supporting policies. We know automated vehicle can negatively impact public health, and we need to somehow govern those negative impacts and reinforce the positive impacts. So we came up with 6 policies or areas that we can impose policies to govern the negative impacts. More details can be found in our papers, which is sourced here. So to wrap up, we have 32 pathways. We could find 32 pathways between AD implementation and public health. Quantifications are required to address the uncertainty in the impacts and the extent of the impacts. And supporting policies are required to govern AV's unintended adverse impacts on safety and public health and reinforce positive impacts. This is what I had for today. Please let me know if you have any questions.
Okay, thank you, Soheil. And maybe you can, like in the public chat, maybe you can add the links to your papers. So if people want to look more into the details, they can check out the papers. But for the sake of time, we need to move on to the next presenter. So thank you so much for that. Our next presenter is from the University of California, Riverside, Zhilu. Please go ahead and pull up your presentation.
Good day, everyone. Hi, I'm Jill Law, an assistant research engineer from CSER UC Riverside. Thank you for attending my presentation. So my talk today is the use of traffic-related air quality estimates to inform health-aware travel route choice. Okay, so in the first day of the symposium, I presented the below exposure routing for heavy-duty diesel trucks. Actually, travel route choice is a decision that we make on a daily basis, from jogging to the park, commute to work, and going out for fun. Route choice can impact our overall travel experience, including travel time, safety, but it can also impact our fuel consumption and our exposure to the air pollution. So can route choice also impact our health? I think the answer is yes. So as an active traveler, we can think, is there a route that can reduce my exposure to the traffic, to the overall traffic-related air pollution? And if I'm a truck driver, I can also be aware of that. Is there a route that can reduce the impact of the pollutant emissions from my truck to the community? Okay, to evaluate the exposure value, our method is fully aligned with the CARTEEH food chain. Generally, we started from the source, the out-of-tailpipe emission, and chain the dispersion and exposure models to the inhalation of the emission. Then we can evaluate how route choice could impact our exposure to the overall traffic emission and the air pollutants. So with this method, no matter if I am a diesel truck driver or a pedestrian by the road, the exposure of the different route choices can be evaluated. So as an example, in 2014, we started engaged in a walkability improvement project led by the city of Riverside. As part of the study, we estimated the neighborhood's PM2.5 concentration from on-road vehicle emissions at 50 meter by 50 meter grid based on the regional travel demand model, and we modeled a number of walking trips within the neighborhood. Here is an example, how can a pedestrian's inhalation of traffic-related air pollution be reduced through route choice? So the results show that averagely during the morning, the PM2.5 concentration from the overall on-road tailpipe emission is higher at these 2 intersections where the color is much more red. If I'm walking from the home, which is on the top, to the school, which is at the bottom, the pink line shows a faster route, and the green line shows an alternative that has a lower exposure value. In the morning, walking on the green route can reduce my exposure to PM 2.5 by 68%. And in the afternoon, if I'm walking home from the school, the green route can reduce my exposure to PM 2.5 by 40%. And as a comparison, the travel time does not increase significantly. And that's some effective low exposure route that we're looking for active travelers. And in 2016, we also integrated the exposure indicator to the bicycle facility planning in the Riverside city. This bicycle planning map comes with the exposure indicator of on-road tailpipe emissions in the south of Riverside city. So as you can see here in the black circle, in the black rectangle, the city plans to build a bicycle lane on this section of Van Buren Road, marked by the gray line. Well, if not considering the exposure to the PM 2.5, the Van Buren Boulevard would be a great bicycle lane addition, given the connectivity to build bicycle facility and the many businesses along the corridor as destinations. But when taking exposure into the account, we found that this segment of Cremeria Road Avenue, 1 block south, would be equally appropriate. In this case, we suggest the city to know more about needs of the community. If there are indeed many school-aged children in the community and they attend the schools over here to the east side of the community, the Cremeria Avenue would be a safer and a lower air polluting exposure route for them to bike to school. Aside from active traveler, we also pay much attention to the diesel trucks route choice. The map here shows the census tracts in red that are SB 535 disadvantaged communities. We have looked at truck low exposure routes at 4 locations in Southern California. 2 of them are also AB 617 disadvantaged communities, which is Carson, Long Beach area and the East Los Angeles neighborhoods. The other 2 case studies are the San Bernardino airport area and the Riverside city area. We looked into the area's population dynamics and simulated conventional fastest routes and low exposure truck routes based on historical street speed, truck emissions, and the meteorology conditions. So maybe the low exposure route still sounds abstract. Here is an example of it. In Carson, this is a trip between an entry point on the major road and a warehouse at the top right corner. The blue circles marks the sensitive locations such as daycares, schools, and several senior housing. The gray blocks in the back show the residential population. The bigger the circle or darker the gray box, the larger the population. We calculated the trips at 10 a.m. at left and 10 p.m. at right. Therefore, we can see those sensitive places, the population at those sensitive places will shift during different hours. And at 10 p.m., the working population returned to their homes within the census blocks. The fastest route is in the coral color and goes around the major freeways. And they're the same between the 10 a.m. and 10 p.m. However, the low exposure route are different due to the shift of population and weather conditions. The low exposure route is slower in the speed than the baseline route. However, the modeled PM 2.5 inhalation reduced about 70%, and the NOx inhalation reduced about 31% in the morning and 44% at night. To note, the low exposure route in this case also saves about 10% of the fuel consumption compared with the fastest route due to the shorter distance and moderate travel speed. This is also a case when the low exposure route and the low fuel route merge into each other. This type of trip with considerable reduction of inhalation and fuel consumption, but slightly travel time increase is what we look for feasibility study in the next step. For this type of studies, the limitations are in the various variabilities and uncertainties. For example, the out-of-tailpipe emissions for individual vehicles are actually changing second by second instead of based on the emission model, which is a constant value through average speed. And the breathing rate for different groups of population, activity patterns for different groups of population at different hour of the day. And the street geometry also plays a big role in this type of routing calculation. And our uncertainties also include the weather conditions and the traffic states, and the stop and the go events at traffic signals on signalized corridors. So our future directions include apply out of the tail, apply the portable emission measurement data and examine the effects of the alternative routes, and couple the benefits of complementary technologies, such as the free signal priority, and the eco approach and departure. And with the founding of CARTEEH, we also aim to develop a metric to characterize the exposure to traffic-related air pollution. And I would like to thank all the CARTEEH organizers and my funding agencies and my team members. If you have any questions, please feel free to contact me. Thank you.
Okay.
Yeah.
Well, thank you so much.
Thank you.
Yeah, I have, I guess, one question for you. Can you comment a little bit more on, like, is this kind of framework used in policy making right now? Do we use low exposure routes in any sort of policy making, like in California? And also, did you guys think about looking more into the health effects or making a more explicit connection into the health effects of, say, the drivers or the populations that use these routes?
Okay, so you're asking if this type of study has been used in any policy making in California?
Yeah,
okay.
Policy making or practice. Like, do we see low exposure routes taken into account in the way, you know, we conduct business and transportation?
Okay, so as an example, in the bicycle facility planning study that I presented just now, we did get together with the city engineers and inform our research with them. And the study locations were selected with the city engineers together based on their bicycle master plan. And we did inform them that, okay, so based on our calculation, these two parallel roads are both very good in terms of connectivity to the bicycle facilities, but when we consider exposure, so the other road would be much better. Consider the bicyclists need more, they inhale more air and they have more intense physical activities. So this lower exposure route could be much better for the bicyclists. So we have informed all our studies to the city engineers for their consideration. And for the other low truck routing area in San Bernardino city, we also been working with the city council when they try to expand the air cargo facility within the city's airport. So we can foresee that in the future, lots of cargo trucks will go in and out of that region. We also use this type of analysis and tell them, okay, so this road will be have less impact to the neighborhood public health. So we have informed all these studies to them, and hopefully we can make a difference, and we can work with the community members to identify a better truck corridors that work well for both of the companies and the community.
Yeah, no, thank you. It's really important research, and you know, it would be best we make sure that practitioners and policymakers can take it into account in some way. Well, thank you so much, Xi. We're going to move to the next presenter, Yuanrui Chang. Thank you. From the University of Texas, El Paso. and he'll be talking about accurately tracking emissions from electric power generation.
Hi everyone, my name is Yuanrui. I'm an assistant professor in the Department of Electrical and Computer Engineering at the University of Texas at El Paso. Today, I will talk about how to accurately track emissions from the electric power generation system. So in this presentation, I'm going to talk about why we need to track emissions from the power systems and what are the current practices for us to do this. What are we doing? So what are our methods to do this? And I'll also present some preliminary results we got so far, and a summary will be provided at last. So why do we need to track emissions from power systems? As we could see from the figure on the right side, this presents all the sources of pollutant emissions. Two very important sources are from transportation and power plants. But in today's world, actually, these two sources are becoming increasingly intertwined. Because of the electric vehicle, because of the transportation electrification. Here is an example for greenhouse gas emissions. Of course, we have different sources, different kind of gas emissions, such as sulfur dioxide, nitrogen oxides. But here is just an example for greenhouse emissions. So for greenhouse emissions, as we could see, transportation takes 29%, electricity takes 25%, so they add up to more than half of the emissions. For these two sources, as I just mentioned, they are becoming increasingly intertwined. Because there's an increasing popularity in electric vehicles. According to the Bloomberg New Energy Finance, electric vehicles will take 55% of the automobile market by 2040. And from this figure, we could see there is a significant increase in the ownership of electric vehicles. During the past decade, it almost went from 0 to 2 million, more than 2 million vehicles sold every year. So this is a significant increase. For electric vehicles, as we know, they don't have direct emissions, which is great. And that's why we promote electric vehicles during the past few years, because we believe it's more environmentally friendly than conventional cars, because it doesn't have any emissions. However, the electric power system is not totally emission-free. Every year in the US, the power system produces 1.5 to 2 billion metric tons of carbon dioxide, and more than 1 million metric tons of sulfur dioxide, and more than 1 million metric tons of nitrogen oxides. So these emissions cannot be ignored. If the power systems are not emission-free, then when we charge our electric vehicles, it's the power consumed is also not emission-free. So that's very important. That's something that we need to evaluate. That's why we need to consider the emissions from power systems, and thus evaluate, and then we could evaluate the emissions, the indirect emissions from electric vehicles. Currently, what people usually do to evaluate the emissions from power systems, the most popular method is through life cycle assessment, basically using historical data to evaluate the the emissions, the possible emissions from production to disposal. This is usually done based on generic data, so it's not site specific. And also for power systems, usually the way we calculate the emissions is to calculate the overall system emissions based on the generation. This is based on how much, let's say, 1 megawatt of electric power generation would induce such and such carbon dioxide emission or sulfur dioxide emissions. So we could, based on how much power we consume from each type of generator, we could calculate the overall system emission. But this is not for a specific location. As we know, the power system is pretty large. There are different locations. The thing is, there are congestions existing in the system, so the emission rates at different locations are not the same. When we think about this, we could use an example. Let's say we have different types of sodas. We have, let's say, some Dr. Pepper, some Coke, some Sprite, and when we mix them in a pitcher and we don't shake them very well, it's like a mixture of everything. And when you pour that drink into different cups, it's very hard to tell how much percentage of drink is Dr. Pepper, how much would be Coke and how much would be Sprite. It's very hard to tell. It's the same for power systems because we have different generators in the system. Each type of generator has a specific emission rate. And when we put all the power onto the grid, it's very hard to tell how much power we consume is from wind power, how much we consume is from natural gas power plant. It's very hard to tell. It's similar to a mixture of drink, which is not well shaked. The thing is that there's still a way to calculate it. It's not as tricky as tracking those strengths because the power flow in the system is governed by the physics of the transmission network, such as reactance or impedance or topology of the network. So there's still a way for us to track the generation at a specific location. That means if we properly model the power system, we would be able to know, let's say at my location, if I use 1 kilowatt hour of energy, I would know exactly how many percent of this energy is from natural gas power plant and how much is from wind farms. In that way, I could calculate the emissions, or we could track the carbon footprint from my electric power usage. So that's what we could do by properly modeling the power system and track the emissions from the system. So what we do is we model the system based on its topology and other physical parameters such as impedance. And we know we have to know where the generators are, where the electricity consumers are. This way we could properly model a power system. So here, in this research, which is sponsored by CARTEEH, this is based on a standard test system that researchers commonly use in electric power. This is a 24-node system. So we have 24 nodes, and there are a number of generators. And also, those circles are generators. So generators are represented by that circle with a small small dot in the middle, and those electricity consumers are represented by arrows. So if you see an arrow in the network, those are actually an abstract form of electricity consumers. It's like power flow goes out there. That's the representation. So in this network, once we properly model the network, we could calculate the power flows on all the transmission lines. We would be able to track, let's say, how much power is from this generator and how much power is from that generator. So we would be able to know exactly the mix of power supplied at a certain location. And based on the amount of power supplied from different energy sources, we would be able to calculate the emissions based on the emission rate of that specific generator or a specific type of generator. Using this method, we could calculate the emissions not only by in a location specific manner. Also, we could do that in real time, because as we know, when we run a power system, the load or the amount of power consumed by customers change all the time, and the generation level changes all the time as well. And sometimes we need to use a different generator, so the emission rate could change all the time. By properly modeling the system, we would be able to do it in real time, so it's not the generic overall data that in this way. So we started working on this project starting this February with the support of CARTEEH. So far we've got some preliminary results, and with the model that we developed, we were able to track the generation mix at specific locations. For example, here, here bus 1, that means node 1. So here, as we could see from the bottom left corner, that's bus 1. Let's say we increase 1 megawatt of load at that location, and then we know the generator, we would have to increase the generation from by 1.03 megawatt from a coal power plant, and we have to reduce the generation from an oil power plant. And also, if we increase the load at bus 18, then we need to increase 1 megawatt from a nuclear power plant, and nothing from the other 2 types of generators. And if we increase our load at bus 24 by 1 megawatt, and then we would need to increase the generation from coal power plant by 0.71 megawatt and increase 0.29 megawatt from the nuclear power plant. With this result, we would be able to calculate the emissions at different locations. Also, we could do this in real time if we want to. As a summary, as we know, with the rising popularity of electric vehicles, more emissions will be induced from the power grid, and that could be considered as an indirect emissions from the electric vehicles. And how we evaluate such emissions in a real time and in a locational manner can offer important guidance for us on EV charging station planning. Using the proposed method, we will be able to evaluate the emissions from the power grid accurately based on the location in real time. That is all about my presentation. Thank you very much. I'll be glad to take any questions if we still have time.
Okay, well, thank you so much for that. I think we will leave the questions towards the end, just because we have 2 more presentations. So for all the attendees, please type in your questions in the chat box or the questions and answers chat box, and we'll get back to it towards the end if we have time. But now, just for the sake of time, I want to move to the next presenter, who is Chia-Hsiu Chang from Johns Hopkins University. And he'll be talking about the evaluation of autonomous vehicle deployment strategies to improve health food accessibility. Please go ahead.
Okay, thank you. Hello, everyone. I'm Todd Zhao, a PhD candidate from Civil and Systems Engineering at Johns Hopkins University. I work with Dr. Tag Igusas. Today, I will present the evaluation of autonomous vehicle deployment strategies to improve health food accessibilities. We believe that autonomous vehicles, or AV, is not just a fashionable technology, but actually have potential to provide social benefits. Our work also launches with a study called South Baltimore Gateway Partnership. The study area is the South Baltimore area, the red region on the map. We met with public officials to discuss the pressing issues that need to be improved, such as traffic inequity. Today, I'm going to focus on the access to healthy food in Cherry Hill, which is the blue circle. The Cherry Hill has severe traffic inequity problem. The rate of households with vehicles is very low, so people rely heavily on public transit. As the table shows, more than half of people take bus to transport. However, the bus service is limited and the shifts are not frequent. This results in the low accessibility to essential needs like healthy food and employment. Here is the feature map of Cherry Hill. The purple parts are the residential areas. The light rail stations connecting to jobs and the grocery stores are both far away from people's house. Three local convenience stores within the neighborhood do not provide nutritious and fresh food, so they cannot be considered as source of healthy food. In sum, Cherry Hill is a typical food desert area where the closest grocery stores is far and most people do not have convenient ways of transportation. We use a simulation tool called Sumo that stands for Simulation of Urban Mobility. Sumo is a commercial level but open source code that is specialized for traffic simulations. The convenient feature is to import traffic networks directly from Google Maps into Sumo interface. And with the demographics and real traffic data, we can simulate very detailed individual travel behaviors. Here is the visualization of Sumo. Sumo can simulate different traveling paths. We can set up cars to represent personal vehicles, as well as the normal traffic flow. We can also simulate pedestrian traveling behavior, such as pedestrian walking on the road, or waiting at a bus stop, or even riding a bus. For this, we can estimate accurate travel times for the residents in Cherry Hill, whether by public transit or AV deployments. To quantify the influence of AVs, we use the Accessibility Analysis Index. The equation is called Average Opportunity Accessibility because we consider the populations of the block group where the pedestrian belongs. We select the accessible grocery store and assign a weight value that's determined by the travel time of the pedestrians. The travel time decay curves on the right-hand side has the decay functions for different traveling purpose and modes. For example, the weight of a 20-minute drive is lower than a 20 minutes public transit because we would like to expect to spend less time driving than taking public transit. We find 3 AV deployment strategies to improve health food accessibility in Cherry Hill. Each strategy has various simulation scenarios and will be computed for accessibility index. First, we will set up the baseline scenario, representing the current situation, where all residents or pedestrians will travel by public buses to go to the grocery stores. Then we have the first strategy, which AV serves as rideshare, like Uber and Lyft. So residents can request AVs to go grocery shopping. The scenarios include different percentages of people using AV rideshare. Next, we assume AVs operate as looping shuttles, because this is a more cost-effective deployment. The AV looping shuttles serves to facilitate public buses, filling the gaps between bus shifts or long distance. 3 routes are developed for 3 scenarios, and 1 scenario with all 3 routes. Finally, we test the strategies that use AVs to deliver healthy food to local stores. So the residents can go to neighborhood convenience stores to pick up their ordered food instead of traveling to the far grocery stores. This table shows the relative accessibility index for the first 2 strategies. We scale the accessibility indices with baseline scenario as 1 to observe the improvement brought by AVs. The AV rideshare strategies obviously has higher improvement, but we can expect when the demand increases, it will cost more to maintain the operations because we might need more AVs. This then will cause congestions if lots of AVs running on roads, and the accessibility index will decrease again because of the long travel time. So the AV looping shuttles is a more cost-effective method, but it is not appropriate for the grocery stores. Because the store is too far away, a shuttle route that covers large area to improve the grocery stores will not be very cost-effective. So finally, we propose the AV food delivery strategies. Use AVs to deliver healthy food to the neighborhood convenience stores. Based on a heat map of relative accessibilities, the improvement is significantly because residents can now travel to local stores in walkable distance rather than far grocery stores. However, no strategy shall be flawless. This work just demonstrates how to use simulation tools to estimate potential risks and unexpected threats for the potential strategies. These simulation results can also be used for further research, like assuredness analysis. The conventional technology will focus on the accurate function performance and safety issues. But we think AVs should not be limited to non-harm. AVs have potentials to provide social benefits, like improved food desert area. So this requires assuredness technologies that deals with complex systems for broad aspects. And the simulation tool can validate and provide insight, and eventually help the decision-making processes of policies. So this concludes my presentation today. Please feel free to contact via emails. Thank you.
Okay, thank you so much. That's really interesting. I think we have time for maybe one question, or maybe one bigger question. First of all, I'm not familiar with the literature in this area. Are there a lot of studies that look at how accessibility to food or changes in food deserts change as a result of autonomous vehicles deployment, or is it a very little evidence base?
Yes, as I mentioned, the condition in the Cherry Hill area is not very good. So there has been a lot of literatures trying to figure out a way to improve the situations, but few of them are about using the autonomous vehicles or autonomous systems to improve. I guess it's a very new research field, and everything is sort of finding their way.
Yeah, no, it seems like it's a new research field, and it's an important question. And I guess the other, maybe not question, but comment I would make is that, you know, access to grocery stores is a health detriment. So something you could think about in the future is whether you want to look at certain health impacts or health effects, or look at, you know, what people buy from those grocery stores and so on. I think that's important as well, and something that we don't know much about, if anything. And just a quick follow-up question, and I might have missed this, so sorry if I have missed it in your presentation, but what does the accessibility indicator entail? Is it just travel time, or is there something else in it?
Yes, we will. We use the travel time to find the weight value, and also we consider the populations where the pedestrian belongs to the block group, because we want to consider average opportunities. Because people live in the same block group may have a similar accessibility index to go to the same grocery stores.
Well, thank you very much. Really important and interesting work. Thank you. We'll move to our last presenter. Last but not least, we've got Hongyu Lu from the Georgia Institute of Technology. And he'll be talking about investigations of moves and AERMOD uncertainty.
Okay, thanks. So I'm not seeing your video now, so please let me know if you cannot see my PowerPoint slides. So my name is Hongyu from Georgia Tech Institute of Technology. We also have Haobing, Tian, Dr. Guan, Dr. Rogers, and Dr. Gensler in our research group for this one. Haobing is actually now a faculty member in the University of New Mexico. I'm going to be quick. I guess I only have 30 minutes. I want to emphasize on the research motivation over the results. So our research actually starts with a very simple question. What input data resolution should we use when we are doing emissions and dispersion modeling? Well, the answer to that seems pretty simple. We should use high resolution data as much as we can. But what if we have to stick to the aggregated data, which is in lower resolution? Does that change our model output? And if yes, how large are these differences? And is there any potential bias issues in here? So we really need to compare the model output derived from the aggregated input versus the model output derived from the high resolution input. And by input, I'm talking about the traffic operations, speed, volume, and fleet combinations. So why speed? Because we have the variability in the input speed. Temporarily, for example, within 1 hour in the morning peak, we could be having every 5-minute beings with different with respect to the average speed. And spatially, for example, we have the fast lane on the inside and slow lane on the outside. And we're not even talking about factors such as managing versus general purpose lanes and the impact of ramps on the outside lanes. So if we're doing the aggregation of speed, we're essentially losing resolution, and as a consequence, we're losing the details of our input data. And these details could be very important because of the nonlinear emission relationships. I'm not going to go too much details into how Moose model emissions as a function of time fraction of on-road engine load. The bottom line is even if we have a small change in the input speed and facility, we can have a large output change in the Moose emission. And that's also the case for the fleet composition. We have the temporal and spatial variability with respect to the source type distributions. For example, we have more heavy-duty trucks on the outside lanes. Actually, on some facilities, they're actually not allowing heavy-duty trucks on certain lanes. And because emission rates vary a lot across these source types, if we aggregate the source type distributions, the fleet compositions, we can get very different output emissions. So we really need to use high resolution data as a baseline in our analysis so that we can compare how large is the impact of aggregating the input levels. So this is essentially a sensitivity analysis in response to the variability in the input of speed and fleet composition as part of the uncertainty assessment. And we need confidence intervals in the end so that we can identify any potential bias we're having here. So our research starts with the development of scenarios as combinations of temporal and spatial aggregation levels. So we're using the high resolution scenario without any further aggregation as our baseline. And we're developing other aggregated scenarios as test scenarios. We're taking the MOOS and AERMOD output for each aggregated scenario, and we compare that with a boost baseline output so that we can have the differences for each aggregated scenario. Then we use bootstrap algorithm for our confidence interval assessment. The temporal aggregation levels we're talking here is 5 minutes, 15 minutes, and 1 hour. The spatial levels is lane by lane, 2 inside lanes versus 3 outside lanes, and all lanes together. So it's 3 temporal levels, 3 spatial levels, 9 scenarios in total, and scenario 0 is a baseline. So why do we split the spatial into 2 inside lanes versus 3 outside lanes? It's because the study site we have doesn't allow trucks over 6 wheels on the inside 2 lanes. So that's the Interstate 285 here in Atlanta, Georgia, which has 5 general purpose lanes, and we did it for every hour from 6 a.m. to 7 p.m. for all the weekdays in April 2019. We got the traffic operation data from Georgia Navigator video detection system, which provides lane by lane volume and speed profiles at 20-second resolution. We converted that into space mean speed and 5-minute means. And we got our fleet composition from GDOT public database and convert that into EPA source types. And for our emissions and energy use modeling, we're using MOOS matrix, which is developed by the Georgia Tech research team by running across all combinations of MOOS inputs. So MOOS matrix essentially generates exactly the same outputs as MOOS without running MOOS, actually, the adjustment. Instead, we're pulling the pre-run emission rates, so it runs 200 times faster than actually running MOOS. So except fleet compositions, speed and volume we just talked about, we're really trying to keep all the other input variables consistent across these scenarios so that we can use them as control variables. And we're taking the output from MOOS matrix as input to our dispersion modeling based on AERMOD. And we're breaking our polygons to match with our spatial aggregation levels. But in addition to that, again, we're trying to keep all the other input variables consistent across our scenarios. So the final step is to do the bootstrap algorithm. It's essentially resampling based with replacement so that we can calculate the 95% confidence intervals to identify potential bias in our analysis. So to give everyone a general idea of how these differences look like, we plotted them in the fundamental diagrams with colors representing the the differences. So blue for positive differences and red for negative differences. On the left, you're seeing the spatial aggregation only scenario. In the middle, it's a temporal aggregation only scenario. And to the right, it's the combination of both temporal and spatial aggregations. So it's really interesting to see the color patterns within each diagram with respect to speed and flow rate. And it's also interesting to see how the color patterns vary across these scenarios. So the bottom line is we're having these differences across traffic conditions. For example, free flow versus congestion versus the transition regime, if you're a believer in a transition regime. So here is a summary of our differences in emissions modeling. So if we combine temporal and spatial aggregations, we could be having differences of up to minus 20%. So what is a negative differences? A negative difference means after we aggregate input, we're actually getting a decreased model output. It's a lower number, which means we're risking underestimation in our analysis. So 20%, I wouldn't say it's large or small, but it's 20%. And if you compare across different aggregation levels, if you have a coerced aggregation level, you're getting a larger differences, for example, 1 hour versus 5 minutes. And if you have a combined aggregation, you're going to get more larger differences versus the temporal or spatial aggregations alone. These are all anticipated by the research team, and they are very straightforward to understand. And we're also seeing differences vary across time of day and across pollutants, which we will cover later. And this is a confidence interval across the hours by scenarios. It's actually not that complicated as you're seeing it. So the bars, mostly in red, the bars is actually the mean value of the differences for each hour, and the arrow bars represent the upper bound and lower bound for the 95% confidence intervals. So to make things easier, if we're seeing for that hour, upper bounds and lower bounds are both below 0, we're 95% sure that we're having an underestimation here. So it's really easy to understand. And if you're comparing across the different scenarios, which is different combinations of spatial and temporal levels, you can see if you're having a more coerced level of aggregation, you have larger differences, especially with respect to the spatial aggregation. And if you're comparing across the hours, that is across time of day, you can also see variance across the hours. Also, we can see variability across the pollutants. For example, you can have a positive difference for NOx for within 1 hour, and for the same hour, you have negative differences for CO, and overall, you have larger differences for CO and PM 2.5. This could be dependent on the embedded MOOS emission rate relationships across the pollutants. And with respect to the dispersion modeling results, we're seeing very similar bias identified in the emissions modeling we just covered. Just look at the red colors across all these scenarios, the upper bound, the lower bound, and the mean of the confidence interval. They're all red, meaning we're risking underestimation under all circumstances for CO modeling here. This is not a surprise to us because we're taking the output from MOOS and use them as input to dispersion modeling. So it's intuitive that we're seeing this bias propagation through the modeling chain. And we're also seeing the same variability across different time of day. Just look at the change of the shades of color and the switch between red and blue. So it's really important to understand that these differences across the days, they don't necessarily cancel each other off just because they're negative and positive. And we're also seeing a variability across pollutants, just like we're seeing in the emissions modeling. I guess I will wrap up my presentation here. The bottom line is we're seeing as large as 15% as mean differences in our model output derived from our aggregated input. And we really recommend using high resolution data as much as possible because we're seeing a bias based on our confidence interval assessment. The bias suggests a potential underestimation, which is not consistent with the idea of being conservative. But it's important to understand that significant doesn't mean meaningful. So an underestimation in your output doesn't mean you're necessarily crossing the line. You have to consider your base values here. I guess that's everything from my presentation. I'm happy to take any questions. I'll start sharing. I'll stop sharing now.
Okay. Well, many thanks, Hongyu. This is a lot of work. I guess my first question is has it been published? Is there anywhere where we can check those results and dig deep into them?
Yeah, we had an uncertainty assessment as a TRB poster 2 years ago and this year as well. But I don't know if they're publishing that poster online this year because of the, pandemic. But I can post. I think I can post that to the chat box if it's not too late. We have 1 minute before the wrap up.
Yeah, no, if you can post whatever links you might have, I personally would like to look more into this. And just a very quick question, just to make sure that I got this right. So it sounds to me like the aggregation of temporal or spatial data overall would result in an underestimation of air pollution levels from AERMOD. Is that the correct general conclusion?
It's for most cases, but it's not always true. If you look at NOx, we're not so sure to say it's a bias because you're actually covering 0 in your confidence interval. So it could be that we need more samples to figure that out.
Yeah. So it's more complex, but there's a general trend for the other pollutants. Okay. Well, I don't want to keep everyone beyond our schedule. This brings this session to an end. I want to start by thanking all of our presenters, our students and early career researchers at CARTEEH for making the time to present this and prepare their presentation for this session. Our next session is the final plenary session, which starts in 15 minutes. Thank you all for attending, and I hope to see you at the final plenary session. Thank you.